So our focus, as I said before, is going to be on image deblurring problem, okay, which is of course an inverse problem, a hard one at that, right? And we would like to solve this. Okay, we would like to know what it takes to solve this. Okay, and that brings in a notion of what is called well-posedness. Okay, what this means is this problem well-posed? Okay, a problem, right, that has to be solved. For example, it doesn't have to be an image processing problem, right? Any problem for that matter that we try to solve, one should first of all ask, is our problem, or is this problem, okay, that has been assigned to me, is it well-posed? Okay. And this notion of well-posedness, right, in the sense that, can I really solve this problem? Okay, then a loose sense, right, that's what it means. Now, this kind of a well-posedness, okay, it can, it cuts across, you see, research areas. Okay, this is not something specific to, let's say, image processing. It cuts across the research areas, and therefore, right, this is a generic question. It's kind of a generic question that can be asked anywhere, anytime for any kind of problem. Okay, and from now on, okay, what we are going to do is we are going to be looking at more abstract things, and these abstract things are not really, not really per se for really a deblurring problem. Okay, these would be generic in nature. For example, right, we're going to look at numerical stability issues. We're going to look at existence issues. We are going to look at uniqueness issues. All these issues are going to be generic in nature, and therefore, for example, right, any kind of a problem that you might want to solve tomorrow, be it in the domain of image processing, be it in the domain of wireless communication, whatever it is, right, that you want to do, you will find that some of these ideas will translate across these areas. Okay, and therefore, okay, when I would like to draw a relation to image processing or image deblurring, I will show that. But then otherwise, right, until such point, right, that I mentioned, whatever we plan to do from now on is going to be generic in nature. Okay, there's going to be these are going to be general ideas, and these are valid for, let's say, any kind of problem, not necessarily the image deblurring problem. Okay, now if somebody were to assign you a problem and say that solve this problem, right, it doesn't mean that you would immediately jump in and say that, okay, right, let me go ahead and find the solution. You first of all ask, is this problem well-posed? Okay, now what is this? What is this abstract notion of well-posedness? So among the various notions that exist for well-posedness, the one that is most commonly subscribed to is what is called Hadamard's conditions for well-posedness. Okay, a mathematician, Hadamard, conditions for well-posedness. So according to him, okay, he laid down actually 3 conditions. And according to him, a problem that satisfies all 3 conditions is well-posed, and even if it violates any one condition, it is one or more conditions, then it is ill-posed. Okay, and of course, one would like to look at well-posed problems because ideally those are the kind of things that you would like to solve. But then, unfortunately, most inverse problems are actually ill-posed. Okay, which is the reason why it becomes all the more important to understand what we mean by well-posed and ill-posed problems. The first condition, right, that he laid down, okay, is as follows. Okay, now for example, right, imagine that right, you have some operator L that is going from a space X to a space Y, so that kind of takes points from X and then maps them to points in Y. Okay, so for example, right, so basically this is the domain of L, X is the domain of L, Y will be the codomain, and the codomain of L, and then right, L maps these points from X to Y. Okay, and of course, one can kind of think about a space, right, within Y, let's call that the range space of L. Okay, which consists of all those points Y belonging to Y, such that there exists an X for which Lx equal to Y. Okay, that is what we call as the range space of L. Right, so Hadamard's condition for well-posedness are as follows. For each datum G in a given class of functions Y, there exists a solution F in a prescribed class X, in a prescribed class X. Okay, this condition is also called the condition of existence. That means if I actually give you an observation, okay, a solution should first of all exist. That means that if I give you a G from the range space of L, then I know that in that case, a solution does exist and there should be some F here. Okay, whether that F is unique and all, right, we don't know as of now, but then existence. But for example, if we give you an F, we give you a G that is outside the range space of L, then we know that there's no F in X such that L can act on that F to give you G, right? So a solution. So Hadamard's first condition is that a solution should first of all exist. Then a second condition is the solution, if it exists, the solution F is unique in X. Okay, so that solution, if it exists, should be unique in X. Okay, this is called the uniqueness condition. And the point is, right, so it's like saying that if you kind of go back to this diagram, I give you a G which is in the range space of L, because okay, then you know that a solution does exist, therefore existence is satisfied. But then do you have just one F that will map to G, or there can be multiple Fs that map to G? Can you have an F1 that also goes to G? If you have also an F2 that goes to G, okay, in which case uniqueness is not satisfied. There can be multiple solutions for one G, okay, for a given G. Okay, that would then make this problem ill-posed. Okay, if the solution is not unique, then of course that would make the problem ill-posed. Now, if you think that, right now, so if you really combine, right, conditions 1 and 2, then it looks like, this is like 1-to-1 and on-to, right? You have a map. If something satisfies both conditions, then in that case, right, you have a 1-to-1 and on-to map, and therefore you can think of L as being, invertible. And therefore, right, one would think, why do you even need one more condition, right? It looks like all should be fine there. If I have a 1-to-1 onto map, then I'm done, right? I mean, I know I give you an observation, and because it is onto, I know for a fact that a solution exists. On top of that, I also right, tell you that the solution is unique. Okay, in which case you're done. For the G, you can always, you're ready to know that an F exists and that F is unique. But the whole point is that Hadamard did not stop there. Right? He introduced one more condition. He introduced a third condition wherein he said that the dependence of F upon G should be continuous. Is continuous, or should be continuous, right? Now, what does that mean? Okay, this has got to do with what we call as numerical stability of your problem. Okay, all these are issues, okay, that we will examine individually. Okay, not just from an image processing kind of a point of view, but in general. And this numerical stability, what this actually means is, if I kind of go back to that diagram that I drew, where we're going from X to Y, okay, this is X, this is Y, and we know that, right, that L is 1-to-1 and on-to, therefore I give you a G from R of L, and then, right, I know that I'm going to give you from R of L, which is the range space of L, therefore you know that a solution exists. So let's say, right, I give you something like G1, and I know that, right, that gives me F1. The point is, right, if I give you a point very close to G1, another observation, just let's say, right, it is very close to G1, and that one is, let's say, G2. Now, because of the fact that this map is 1-to-1 and on-to, I know that G2 will not map to F1, even though G1 and G2 are very close. I know that, right, when I go back, when I inverse map, I may get some F2. Now, right, 1-to-1 and on-to-ness will ensure that G1 maps to F1, G2, right, even though G2 is very close to G1, will not map to F1, it will map to F2. But now this third condition, what it is trying to say is that if G1 and G2 are very close, then my solutions F1 and F2 should also be very close to one another. Otherwise, it's an ill-posed problem. Okay, which makes a lot of sense, because what this means is that even if there is a small amount of noise that you add to the observation, and that takes you away from the solution in a sort of a significant way, then it means that right, you have an ill-posed problem, right, because it's numerically unstable. Okay, so you would expect that a small change in the observation should lead to a small change in the solution, right? Otherwise, solving the problem makes no sense. Okay, so these three conditions are what are called Hadamard's conditions for well-posedness, and even if one of them is violated, then you have what's called an ill-posed problem. Now, most inverse problems tend to be one or two or all of them, right? They would basically suffer from all these three conditions typically. Okay, and therefore, right, one needs to find a way out. Okay, the most general way out we will find later, but then some of the simpler things, right, that we are aware of, that we kind of tend to do, is what we will see first. Okay, so let's first examine this notion of what is called right existence. Okay. Okay, and the point is, right, if a solution is not really guaranteed to exist, like for example, right, I mean, it's like saying that if I'm trying to solve ax equal to let's say y, and right, if I give you now the existence thing, right, is more like, okay, now yeah, so suppose A is m cross n, okay, this is n cross 1, this is m cross 1, okay, and then suppose this y is not in the column space of A, right? Then we know that a solution does not exist, right? So we have an inconsistent set of equations. Okay, so right, in such a case, okay, you may not be able to solve for x. Okay, a solution does not exist. But then, right, point is, we don't really stop there. So it's like saying that if I go back to my example, okay, that I drew earlier, it's like saying x, y, and the point is that if I'd given you a y that came from the range space of L, then of course the solution would exist. But then you know, due to noise or some other reason, if I'm outside and I give you outside of R of L, right, then we know that right, that there's no way, there's no vector here, right, that can be acted upon by L in order to, right, give you this y. Correct? So when y is not in the span of the columns of A, right, and of course, you know, we would try to, because for us it's all about matrix, right? I mean, all our operators are typically linear, the blurring operators, everything is typically linear. Therefore, we would want to look upon this L, okay, as a kind of matrix for us. So we want to solve something like Ax equal to y, and normally, right, what can also happen is, the other case that can happen is, we've got like m much larger than n, okay, which means that we have an overdetermined set of equations. And therefore, right, I mean, a solution need not exist. In such a case, what do we do? Well, one would expect that if I cannot find a solution because of the fact that this is outside of R of L, what I could then do is, you know, find something that is closest to y, right, in R of L, and therefore once I land here, right, then I can always go back and find out, right, and I can always go back and find out an f for this, because an f for this will certainly exist, because once I come from y to y dash, and y dash lies in the range space of L, then I know that y dash will have some solution f dash. Now, whether the solution f dash is acceptable to us or not is another issue, right? I mean, how close y and y dash are, and therefore whether this f dash is something that we can accept is some other issue. But the point is, right, we typically do not leave a problem unsolved just because it is ill-posed. We try to make every attempt to at least get some kind of an approximate solution. Now, the most common approximate solution, right, when you have a situation like this, is what is called linearly squares. A linearly squared solution. What is this linearly squared solution? So it says that if you cannot find an x such that ax is equal to y, if you cannot do that, then try doing this, right? Try minimizing, okay, with respect to x, this function norm of ax minus y square. Right? So it's trying to say that try to pick an x such that the norm of ax minus y is as small as possible. That means try to pick x such that ax is as close as possible to y. Okay. Now we can actually define this cost as j of x. Suppose we define this cost as j of x, and then we write it as ax minus y norm square. Then this becomes ax minus y transpose into ax minus y, which in turn becomes x transpose, A transpose minus y transpose into ax minus y, which in turn becomes x transpose A transpose ax minus, of course, you should realize that x transpose A transpose y and y transpose A transpose x are both scalars, and each is a transpose of the other. They are both scalars, in fact. Therefore, you can write this as minus 2 y transpose ax plus y transpose y. Okay, this is y, of course. This is y transpose. Okay, and in order to find an optimal x, we can do dou j by dou x. Let's equate that to 0. And because of the fact that x is a vector, right? Please note that right, x is a vector here, even though I'm not underlining it per se. But x is a vector, and therefore, right, when you take really a derivative, with respect to x, that is a vector, what you will get is dou j by dou x. For that j, it will turn out to be, see for example, right, you should know that right, in general, if you do d by dx, where x is a vector, of y transpose ax, where y is not a function of x, y is a vector, a is a matrix, then this will be equal to A transpose Y, right? This is something which is easy to show. We can just take a small example, take a 3 cross 3 or 2 cross 2 and show this. On the other hand, if you do d by dx of x transpose Ax, where instead of y you got x transpose Ax, this is equal to A plus A transpose X. Okay, this is again something, okay, which you can easily show. So now if you apply the same sort of principle here, why do we take dou, right? We can as well take djx by dx equal to 0, and therefore djx by dx will be, the first term is x transpose A transpose Ax, and A transpose A is symmetric, therefore right, this will give you 2 times A plus A transpose is 2 A transpose Ax, and then we've got minus 2. Okay, this is y transpose Ax, and we know that d by dx of this is A transpose y. So minus 2 A transpose y, and then the last term is a function of y, and therefore this simply goes to 0, and therefore what you have is A transpose Ax is equal to A transpose y, which in turn means that you've got x to be equal to A transpose A inverse, okay, A transpose y. Okay, now this is your x hat. Okay, so the optimal value, okay, the optimal x hat, right, the optimal x hat that you will get under a least squares condition, okay, is this. Okay, so your linear least squares solution is this, and of course, right, and of course it's not true that Ax hat is equal to y, right? It won't happen because of the fact that y is not in the span of intercolumn span of A. Okay, so Ax hat is not equal to y, but then this of course Ax hat will give you some y hat. Okay, Ax hat will of course give you some y hat, and then this y hat is such that it is closest to y. So if you go back to this figure, right, you've got y here, you've got y hat in the range space of L, therefore y and y hat. So y hat is such that y and y hat are very close. So this error vector has a smallest norm, right, because this can be looked upon as the error vector, and therefore this solution x hat is such that this error vector has the smallest norm. Okay. Now, there can occur a situation when, let's say, when you may not be able to see invert A transpose A. Okay, when you cannot invert A transpose A, it means that the columns of A are not linearly independent. When that happens, right, we have to find another way out. But for the time being, let's just assume that A transpose A is invertible. Okay, and then how to solve the case when A transpose A is not invertible, or in other words, the columns of A are not linearly independent. Then in that case, right, we'll see soon. Okay, so something like this is is called really right, this is your least squares estimate. Now it's interesting to see that y hat, right, if you see, is A times x hat, and therefore this becomes A into A transpose A, the whole inverse. If I just substitute for x hat from here, it becomes into A transpose y. Okay, now this is your y hat. Let's call this matrix as P. Okay, now this P has some interesting properties. Okay, look at P. Now P is A into A transpose A whole inverse into A transpose, right? So P is equal to A into A transpose A, the whole inverse A transpose. Let's try finding out what will be P square. P square is P into P, which is A into A transpose A, the whole inverse A transpose. This is P, and then follow it up with another P, which is A into A transpose A, the whole inverse into A transpose. Now these two will cancel each other off, and you will end up with A into A transpose A, the whole inverse into A transpose. But this, we notice this but is P itself. Now what about PQ? PQ will be P square into P, but then P square is equal to P, therefore this P into P, this is equal to P square, but P square is equal to P. Right? Therefore any P raised to N is equal to P. Okay, and such an operator is called an idempotent operator. Okay, it's called an idempotent matrix. Okay, this is called an idempotent matrix. P is an idempotent matrix because of the fact that P raised to N is equal to P. Okay, now this idempotent is really a notion, okay, which is more generic. It doesn't have to be only for matrices. For example, you can also have nonlinear operators, right, which are idempotent. For example, taking max, taking min, right? Max of a set, max of a set, right? So for example, if you have max of S, right? If this is equal to A, then max of S is also max of S, right? Is also equal, right? So if you say max of S, right, is equal to A. Okay, so max, min, all these are idempotent operations. Now, when because of the fact that P is a matrix, right? So P is also a matrix for us, right? It's not simply some idempotent operator. It is a matrix, and therefore, right, because of the fact that it is a linear operator, so P is called a projection matrix. A projection matrix. Okay, why? Because of the fact that it really takes y. For example, in this figure, it takes y and so P projects y to y hat in RFL. Correct? Okay. Now, one more interesting thing is, right, one would want to check, okay, is this error orthogonal? Okay. So for example, right here, okay, in this diagram, there is error which is y minus y hat, right? So one can ask, is this y minus y hat, right, orthogonal to RFL? Okay, now in order to check that, right, what we can actually do is, let me just take this example. So suppose we ask the following, okay, is y minus y hat, okay, y minus y hat transpose y hat, okay, this is equal to 0. Okay, because of the fact that y hat is an RFL, right? So we're asking, so right, we had this, okay, we had a y which is outside, we dropped it, we took this P operator, P matrix, that is a projection matrix, applied it on y, got your y hat. Okay, and here is your error, which is y minus y hat. So we are asking, is y minus y hat orthogonal to y hat? Okay, when is this orthogonal? Now substituting for y hat, so y hat we know is but p operating on y, right? Because P operates on y to give you y hat. Therefore, y minus y hat is py transpose y hat, which is actually py. Okay, is this equal to 0? This means that y transpose minus y transpose p transpose py is equal to 0. Or in other words, y transpose py minus y transpose p transpose py, okay, is equal to 0. But then we know that, okay, now if p transpose is equal to p, okay, in case p transpose is equal to p, if this is true, if it so happens that p transpose is equal to p, then p transpose p is equal to actually p square, right? Now if you go back to this matrix, it's easy to check that or verify that p transpose is equal to p. Okay, when p has this form, it's clear, right? It is clear that p transpose is equal to p, and therefore p transpose p is equal to p square. But then we know that for this p square is equal to p. Therefore, it so happens that you have y transpose py, and this whole thing becomes y transpose py, and therefore this is indeed equal to 0. Okay. Therefore, because of the fact that this error is orthogonal to y hat, such a p is also called an orthogonal projection. It's called an orthogonal projection matrix. Okay, you can also have something like an oblique projection matrix and so on, but then we are more interested in this, which is really an orthogonal projection matrix. For example, something like which is oblique would look like, oblique will be like 0 0 alpha 1. Okay, you can check, for example, p square is equal to p, but p is not equal to p transpose alpha not 0. Of course, if alpha equal to 0, then you're back here to an orthogonal projection. Okay, so such a thing is called oblique projection, but then, right, this is not something that we will be interested in doing, but just for this information's sake.